So this is a lecture number 9. We are going to discuss regression and regularization. Okay. We will talk about the regression methods, linear regression model, least squared algorithm, and then mention this optimization. Regularization, and we will discuss rigid regression, lasso, and the elastic net. Okay, so at the end of this topic, you should have general concept of all of this. They're important, and maybe at the very beginning, you when I mentioned the regression, linear regression, you may feel familiar with, and then we will go into the detail and how these parameters like beta will be determined and estimated. Then you may not be familiar with regularization, and because I don't know, as a biology student, have you ever been taught about lasso before? No idea. And those are the techniques we can deal with overfitting problems if you have many features. I mean, independent variable you want to use to explain your a lot of parameters to explain your dependent variable. In that case, you want to have a way to select which variable, which feature are most important ones. You keep those and get rid of those less important ones. How are you going to select this procedure to help you to deal with this overfitting problem is called regularization, and working on the parameters. Okay, as I said, you may be familiar with this linear regression, and more or less in your statistics class or whatever your language learning procedures, you will have encountered this. And so the idea is you have an independent variable. You want to use this to predict dependent variable. In that case is x-axis are the independent variables, and points here are the samples. And then you want to fit that those points with a linear line, regression curve, and try to predict what's the y variable value is by giving the x values. Okay. So when we talk about a line, you will have parameters like slope and intercept, and then try to use this to define a line, which that's what you have this statistic table in your summary table of the linear regression. You always have the estimates for intercept. That's your intercept. That's this value is slope regarding to this variable, right? In this case, is just one variable, single variable. That's very easy, and you can have multiple different features, different independent variables, and you can incorporate into the model to explain your y. You can do this very easily. Most of this statistic package have this even in the Excel sheet, spreadsheet. You can follow the procedure to calculate the deviation from your predicted value. And then what's the difference? You try to minimize the difference between your actual value and the expected value, so give you the best solution. So you can do this. And in R, I believe there are packages to do. And in Matlab, you can have a fit linear model, the function you gave. If those variables, try to explain y. In this case, MPG, the variable is a y. You want to explain using x. X is a multi-variable matrix, then you need to have a certain number of samples. If you don't have enough samples, you don't have a good solution for this estimate, right? Okay, so that's your impression of this. So we are going to using this familiar framework and we translate this into a linear algebra, so you know how to calculate this. Just use basically we want to calculate the beta values. The beta value contains the slopes for different explaining variables, and which one contribute most, which one contribute the second, depends on the value of beta, right? Okay, so in the machine learning framework, and this regression belongs to supervised learning, and we talked about unsupervised learning. The clustering is example, and the classification, because you need the training data, you have to build your classifiers, and that's supervised learning. Regression belongs to supervised learning because you want to use samples. Your samples are your scatter plot of the data points. You want to use these data points to estimate beta values to fit the model to give you the best predictor, and you can regress and to predict the next value. If I give you all the information you need in the feature or in the explaining variables, you should be able to predict the y, which is dependent variable. So this is a technique to model and analyze relationship between variables, between your explaining variable with the dependent variable. All right, essentially we want to find a function. This function will take x as input and give you the y, the output. So if you only consider one variable x, and this will be a vector, and the elements in the vector are the samples, and this is sampled from the population, and x is the value for each independent sample, and then y will be also a vector, and that's your predicted value. Okay, in that case, we don't know how can we solve the problem, how can we find the function, so that's uncertainty, and so we need to design a loss function to give our standard to see whether this function is good enough, or what kind of parameters should be in that function to establish a relationship between x and y. Okay, so x can be multiple variables, because you oftentimes want to use more than one variables to explain the relationship. Each variable contribute differently and to predict the y value. In that case, you have a p dimension of features, okay? You can think about this samples as data points and the p as p numbers of features. Those make the matrix. So x could be a matrix. In this case, y is always a vector, so y is, otherwise we will deal with multivariate problem. So I will explain that later. Okay, this formula looks like this. We want to have a loss function, and this loss function indicated by this capital L. So I want you to familiar with the sum of this. So this is a loss function here, okay? This function takes two input variables, put y, so this should be lowercase y, because if you use lowercase as a vector, it's always lowercase, but it's okay. And that's a function. This function, you establish the relationship between x and y. So that takes x. So this will give you the prediction of y, right? Okay, so the loss function will look at your prediction, your predict the results against the real observation, and we will calculate the difference between them. And then you want to estimate this difference, and you found the relationship between them to minimize this estimation of the value of loss function. If you can find the combinations of function f parameters to give you the minimized level of estimation of the loss function value. So that's the indication of this, indicated by that. So that your objective. You want to minimize the difference between your predict and your observed y. Okay. Any questions for this? Easy. It's just the framework. Okay, if there's no difference, so you predicted perfect y is y, and then your loss function should be 0. Okay, this lowers the value you should have. The most commonly used loss function is this. Okay, so we know this 2 vertical bars means norm. Okay. So this 2 here indicated called so-called L2 norm. L2 norm is very similar. It's just equivalent to the way you calculate Euclidean distance, right? You calculate Euclidean distance by take the element inside this node, this 2 bars, and take square and sum them and take a square root. Remember that? This 1 square, square. So that's called L2 norm. So that's why you gave a 2 in the subscript here, indicate, okay, I'm calculate this norm, but I calculate L2 norm. I didn't mention it because I don't want to make you confused, but today we need to know L2 norm, L1 norm. Okay, once I compute L2 norm, so if I don't tell you which norm I calculate, with the type of norm I calculate, by default, I'm calculate L2 norm. So you can indicate L2 norm here by writing this 2 here, and also there's another 2 here that indicates the square. Okay, I want to have a squared norm to minimize this. So I believe norm 2 already always positive because you have not so sure whether L2 norm is always real or positive. It could be a complex number. I'm not so sure. But anyway, so you gave the squared guarantee is positive real value. And there are also yeah, so that's the way so-called least squares. So the name is here. Okay, you need the squares in there. Okay, you have seen this again and again. So this is a norm, right? So that's what I write here. This is called the L2 norm. And here you have dot product or inner product between 2 vectors. So if you have the dot product, and the result will be a single value, and then that will be the element between A and B, and multiplicate and then sum. So you have this form. Okay, so you can write out like this if you have two elements in there. So x1 times y1 plus x2 and y2. Okay, so we know the norm and the dot product. Now I'm going to define a dot product for two vectors. These two vectors are beta and x. So if you have these two vectors, and you can write dot product between beta and x. In this case, x is a vector, and then this will be you transpose beta and make it a horizontal vector times this, or the other way around. Anyway, so this will give you the product which is that form. So that's just two elements in x vector, and then you have this form. If you have three, so one is a very special, and this will give you the beta value which independent from any x in that case because it times one. So this one just make this beta 0 standing out. So this is intercept actually, if you consider this as a linear combinations of variable x and y, and that's parameters for them. So this dot product between beta and x is, if you consider this as a linear variable regression model, then it's using this model to explain, to predict the y value. You can say, okay, I just represent the model in this simple way, right? Dot product between two vectors. Any questions? No. By the way, this is just one vector. This will be just one sample. One sample. Normally, we'll deal with p samples. So that will be a vector, not only not a vector, but you have to concatenate a lot of those kind of vectors, and then that will give you the subscript for those x1, 2, y2. So you have you make this into a matrix. That will be next slide. Okay, we come back to the norm. So I already explained L2 norm. That's what we always, so far we always talked about. To indicate this norm is L2 norm, you put a subscript 2 here. So what is L1 norm? L1 norm is very simple. It's all the elements absolute value put together. No square, no square root. Okay, so if you have a vector, and what's the L1 norm for this vector? So you just take x1 plus x2, x2. So you have to do the absolute value first. So that's just the total absolute value, that's sum of total absolute values. Frobenius norm is for matrix. You treat matrix as a vector, and then you have this forbidden norm. Essentially, you just have a multiple columns. You linearize those vector, makes it very long vector, and that's your two norm for that vector is your two norms for the matrix. I mean, it's L2 norm applied to matrix. Okay, so we also you should also familiar with this Unicode unitary circle, right? So here, this point is 0, 1, 0. This point is 0, 1. This is 0, minus 1, 1, 0. So all the points on this circle have L2 norm equal to 1. So that's gave you this shape. Well, so if you try to define the points, all the points have L1 norm equal to 1, then those points make this square, and yeah, okay, so all the points on this have L1 norm equal to 1. Okay, this is Unicode Unitary. So if you put unit circle and this unit square onto the same coordinates, then you have this. Okay, just remember this for now, and we are going to use the parameters for this, and all the points, by the way, all the points inside is a circle or the square. Those points have their norm L1 or L2 norm smaller than 1, right? Or the point outside this circle or those L1 norm, L2 norm greater than 1. Okay, so at this point, we already prepared ourselves with all the linear algebra and these notations. We are going to see, okay, how can we define simpler linear regression model and the multiple linear regression model? Okay, this should be very similar to what you know already, and you use beta 1 as intercept, beta 0 intercept, beta 1 slope, and then you have x1, the only single variable to explain y, and in that case, it's called a simple linear regression, or single variable linear regression. But oftentimes we'll deal with multiple linear regression. Remember the name, okay? Multiple linear regression, you have more than one variables, independent variables. You want to give each variable a parameter, a weight or beta value or slope regarding to this particular variable, and also intercept to predict y. A single example of this is you want to predict y, which is the price of certain type of car, and then your input variable, you try to explain the y, try to predict the price is the size of the engine, and then you use simple linear regression model to build a relationship between them by calculate from samples different cars. Okay. In this case, this is beta 0, this is beta 1. So you have y plus 0, 1, x. Okay. Well, x is the engine size of your sample from different cars. If you do this one by one, so you have each y, you have one sample, then you can write out each individual equations, or otherwise you just write in the matrix format. It will be just do that. Okay, in the multiple variable regression, linear regression model, you have y is the price you want to predict. Here you use engine size, horsepower, and the peak RPM, length, weight, height. So you have those independent variables, and you build a model. You have beta 0 for the intercept, beta 1 for first variable, beta 2 for second variable, etc., etc. And you build that model. Again, you need data points. You have samples to predict those values and to give you the estimate of your parameters. You have negative parameters is the length, and that have a negative impact on the price. Okay, now we write this into a matrix format. Matrix multiplication. So you have y, you sampled n numbers of sample size. Okay, if you look at only the first y, so that's your first car and how much it is, and you want to use the variable of X matrix, the first row, plus all the weight of each variable to predict y. So you have multiplication between this vector and that vector to give you y, y1. And then you repeat this to predict y2 using the second row, the sample, and still you have a shared beta value because your beta is estimated from all the samples already. So that's the beta value was shared across all the samples, your model estimation. And then you multiplicate this dot products, give you y2. You do this iterate one by one. And y is in the first column, so this beta is intercept, it will not change. Okay, so you don't have to write each sample point one by one out as an independent equation. You can just use the matrix of X multiplied by the beta vector, and then you have the prediction of Y. Okay, in order to make this work, you need to do some transformation to make sure you are right. You have a p, if you have a p values in the beta vector here, and you want to make sure you can do this multiplication. So, so that's inner dimension, and so n times p plus 1, because you have p variables plus 1 intercept variable. And then this times the beta is p, the dimension of beta is p plus 1 times n, times n times 1. So if you do this multiplication, you end up with a vector. So this gives you a vector n by 1, 1 by n. Okay, so this vector n by 1, n by 1, not n. This vector should have the same dimension as your y. The y is your observed, and this is your predicted. So the difference between y minus x times beta is another vector of n by 1. This n by 1 vector is the difference between observed and your predicted by your model. So that's error, basically. Does that make sense? Okay, your observed vector, or the price, minus your predicted value of your price of the car, and then difference is how accurate your prediction is for each individual cars, and those difference are those errors. Some may be just 0. It indicates your model just predict that value perfectly, but most of this should be have a small values, either positive or negative. You overestimate or underestimate the car price. Okay, so this is the most important equation then, because this is the difference between observed and predicted. That's a deviation, or that's your errors. And we optimization function will try to minimize this, the total value of this. Okay. So to write them out, if you decide to put them together numerically, this equation is this. Okay, that's just I explained it. So here they include these arrows inside the equation, so it makes them equal. Okay, any questions? Yeah, so I think all this concept you know already. We just rewrite the equation to present them in the way like in algebra. Another example, we have two factors to predict x1, 2, and then I try to predict yield as y. And in this case, you have search space of variables x, y. So you want to have combinations of x, y, and give you the value of z, x1, x2, and give you the value which indicated by y here. And those values combinations forms a plan here. Okay. So our linear regression model, the purpose of the expect, you want to estimate those parameters to give you the relative contribution from x1, x2, and also this intercept to give you the about to move this to the average of y. So that's our purpose. We try to build this model. So if we have observed the data points, we have variables. Our goal is to find the values of this. These values makes a hyperplane in this case because we have only two variables. We make a plane. Otherwise, will be a curved surface in a higher dimension. But anyway, conceptually, you want to estimate those values to give you the best fit. So what is the best fit? It's your predicted value, the difference between observed. So that's your observed. You have a predicted. So you want to minimize this, okay? Okay, we quickly jump to the keywords of explanation make a difference between univariant and multivariant. So when we talk about when we have this variance, especially you have multivariance, that means you have more than one output variables. So remember, we always have a linear regression model or multiple variable models. Output is always just one vector y. But if you have multiple vector predicted, all those analysis called multivariant. So don't be confused by the multivariable and multivariant. So this slide just want you to make sure you know this. They are not inter-exchangeable, and so when you write your abstract or something, make sure you know what that means. You really mean you want to do multivariant regression, then you use that term. Otherwise, you always use multivariable will be safe. Okay. So this is just for your information, not directly related to our topic today, because we are not doing multivariant regression or multivariant analysis. Okay, so next we are going to explain how can we estimate the value of beta. Because once we have data, when we have model, we want to estimate the beta to establish this regression model complete. So we can use this as a predictor for the future, or we can use this to detect abnormal data points. Okay, if you have an outlier and some data points just not fit this regression line very well, and we know, okay, those are the outliers. So there are a lot of applications, and we may not mention them today, but in single cell, in single cell analysis, I will mention some of them later. For example, for those to use the deviation to detect highly variable genes. So we will fit simple linear regression curve between genes expression mean and their CV across all the cells. So once we have a population of genes, we can use that curve to detect the deviation of each gene's deviation from the expectation, and then we can find those highly variable genes which have a higher than expected coefficient of variance, for example. Okay, the application will be followed. In this case, so far, I will to show you how can we use linear algebra to estimate the beta values here. The example I'm giving here are the perfect 3 points, and these 3 points are landed on the single line here. This, and you can define beta 0 and beta 1 to define this this straight line, and then this 3 example data points are perfect fitting on there. So in that case, you have if you give 3 x1 3, and then y1 is 4, so this point. If you gave 0 as x2 and y2 is 2. If you gave -3 as x3, so you have 3 samples. So we need an equation. We need estimate beta 0, beta 1 to make them to make 3 of these data points to satisfy this relationship. Okay, if you write this in the matrix way, and then that will be x input 3 0 -3 and times vector beta 1. This is single value because we only have 1. Okay, so beta 1 beta 0, and then the output should be this. So we write beta 1, beta 0, beta 1 into a vector. So this should be beta 1 times this, give you y. So that's what we want to have this perfect solution. So how can we do this? So it looks very easy. So if you have a relationship like y times x, so y just don't have beta x minus 1. Right? Can we do that? So let's give you the solution of beta numerically. Right? In reality, we can do this, yes. And if we solve this, we will achieve almost the same optimization problem, the same solution. Okay, we come back to this loss function definition. This is just write in a slightly different way. So now you have n samples. You calculate the difference between each observed and its prediction. And then at the end, so this will be errors, a vector. So you sum them all together after squared. Okay, so this is called squared root error. Sum of squared errors. Basically, you want to find combinations of beta vector values to minimize your sum of squared error. That's observed. This is predicted. The p variables and the squared here. Okay. Any trouble to explain this by yourself? Okay. Yeah. Just slightly different format of the writing, but the same idea, same optimization, same loss function. Okay, as I said, our model is this. Can we just directly solve beta value by put 1 over x times y? Okay, inverse X. X is a matrix when you have multiple vectors. If you have multiple variables, in that case, we need to have the matrix inversion to solve the problem. Then you can directly give this. Here I use another example, but you should be able to use the previous example the same. So you have those data points on the straight line here, and you have a, here I only use 2 and 1, 3, 1.5, and then output this. And you can calculate the beta values. So beta 0, 2, beta 1, 0.66. Okay, indeed you can use inverse of X matrix and times Y to give you a beta value. By the way, the definition of inverse of the matrix is the matrix times its inversion, and will be the identity matrix, which 1 in the diagonal and all the other places are zeros. So it's not it's different from the 1 over the n. So if you have n as a okay, as we said, we try to use least squares, which is this your model, linear model, and you have a predicted values. So you have this straight line here, and then for any given x value, you should be able to predict y. But you observed the difference between your observed and the prediction. You can find it by calculate the difference, and then that's indicated by those yellow bars, that the difference between observed points to the prediction. And then because this value have a positive, negative values, so once you square them, then it become all positive, and then you sum. So this is least square. If you minimize this, then change the parameter of define this curve, this line, and then you get the best solution for the estimation of beta value. You can try different beta values, different slopes, and they give you the best, the minimized value of this, and then that's the least square method and the ordinary least square method. Okay, so those difference squared and sum have the name, the residual sum of square, RSS. So beta is for any combinations of beta values. So this change the value. If you have different betas, then you change your prediction, and then the difference also changed. So RSS is a function depending upon the values of beta. So that's why you can see, I want to estimate from my data points and give you the best combinations of beta values to minimize RSS. Okay, this is the whole idea of this. Okay, to write this into matrix format, that will have y minus x times beta. And the square root of this is the same as the dot product of that. Dot product of itself. Okay. So you can write RSS as this. So the next statement is not so obvious. So that's I'm going to derive why that's the case on the blackboard here. So that's called derivation of normal equation. But you can just remember the conclusion. So if you want this to be minimized, and you can have this relationship, and the beta will be t minus 1 t times 1. Okay, so this is called normal equation. So using this relationship, you will get the estimation of beta as a function of x and y in this way. So here are some other statements around the normal equation. So remember, they here they use w to replace beta, but it's the same. So estimate beta should be the best should be this, and then the way to estimate is to minimize the error once you give in the combination of the beta. And at the end, the solution for the beta is this. Let me see whether we have time to write this. So I'm going to show you why this is the case using some of this calculus solution on the board. Now we'll first write a couple of the rules in the matrix differentiation, and then we can take a break and come back and continue to derive this relationship, why you can use this equation to calculate. Actually, we missed one of this. To calculate the beta value directly from x and y. Okay. So rules of matrix differentiation include so if you have if you have a beta matrix, beta is a vector, and you have A, so we use A as a general term for you have X. Let me just use X. That's your beta matrix. If y, if you have a function and y is x, then there's no relationship between y and beta. Then the derivative of y beta. So this will be, so this relationship will give you 0 here. The y is not dependent on x. Nothing to do with beta. However, in this case, if you have x beta, then derivative. So I'm not going to copy that. I just gave you this. This will be x. And if you have y, this gave you the same derivative of this is it's transposed. So this transpose matrix. But this is just some rules I'm not going to illustrate further. It's just. But we are going to use this simple relationship. The derivation of the normal function. So this will be beta, in this case, transposed. You have this relationship, then this partial y, partial beta, this will be 2x. Okay. There's some general relationships we are going to use later. Okay. Another, I believe, if you have x, you have a transposed. This is transposed. So I'm going to show you. This is true in Matlab. That's the relationship we also need. That's all we need to rebuild the normal equation. Okay. So now in Matlab, I'm trying to make the case of this numerically correct. So if my x is a random number 4 times 5, my b is random vector for 1. Let me see. 5. Okay, my x times b is this. My b transpose times x transpose. Yeah. I think that's what I really want to continue. Yeah, I think that's what I try to see. Okay, this transpose can be transpose is, so you change, these are the same, right? Okay, it's time to take a break. So I just approved if this is true using 5 minutes break. Okay, we continue, and we need to have RSS as a function. Residual of the squared sum squared error, and this function will be a function of beta, right? So this is the error. Basically, is the sum of this error squared examples, and this. If you write into a matrix format, it could be error. Okay. So error is vector of that. Then the function of that is, so that the beta. So assume we just only have one beta, but it is represented. So this RSS. And this change of RSS with beta could be something like this. And we try to find a place where the change of beta have no impact on RSS. That place is satisfied this derivative of RSS partial of beta. In this place, that's our solution, and we try to find a function this point, which provides a solution of beta combinations to give the smallest value of RSS. So we want to have RSS function of the derivative of this become smallest as a 0. Okay, it's unchanged. So this can be write as y minus x beta times itself. Okay. Then I have to expand this. This becomes y. T times y. T means transpose, right? And minus y. T into this. Minus y plus so I can actually prove this in Matlab if I plug in some example data. So this numerically, just a single number will be same as that. And it just expanded this slightly different. Here, the transpose of this times that would be this. I use the relationship between that, rewrite to this transpose and rewrite in this way, and use this relationship here. Okay, so that's the equation for this. So now I'm going to the partial of RSS partial RSS. Partial beta. So I want this to be 0. So I need to know what this is. And to apply those rules here, and this stuff, you can think about as X. Okay. This stuff variable and it's 0. There's nothing to do with beta. 0. And so I'm doing the this. And then this one here, I use 1, 2. So beta is here, and direct will be this one. Okay. So in this case, I just apply those rules, and for the derivatives, each of them corresponding. And to make this as 0, so we need at n, we have then one transpose that. And okay, so that's what we at the end we need. Okay, just apply those rules and to make this derivative to 0, and then plug in everything, and then eventually get this. So this is called a normal equation, and we can, if you have x and y from your data, you get data to values. Okay, so we can try this using real data. So that's some real example data, and then you just plug in this equations directly. Well, here I use Julia, but Julia very similar to to Matlab, and then you have exactly the copy of this. So you have X transpose times X times inversion and times X transpose times Y, and give you the beta. In Matlab, we used so-called pseudo inversion to facilitate the computation of the inverse. So that's an example. So in this case, we have Y, we have X. If you want to use a built-in function to solve this, and you have two variables, X, Y, X2, you build a model, you can get the parameters of Y. Another way is to use this shortcut and this backslash operator and give you the beta values. Right. So all these are the equivalent. You get the same answer. You can use this equation. It's directly translate normal equation, and then you have X transpose times X inversion times this, and Y. That's why here you can use the pseudo inversion to replace the inversion. It's more computationally, more flexible, and give you less errors if you have an unbehaviored matrix X. Or you can even write more similar to the equation itself. You have this negative power, -1 power, and this to replace the inversion. Or you can directly use this inversion and pseudo inversion on that. And the pseudo inversion was calculated through SVD, and the SVD will explain next lecture. Okay, that's one of the application of SVD decomposition. But anyway, so this is a numerical example to give you the idea about using normal equation to solve the to estimate the beta values for linear regression problem. The limitations, and you need more samples than variables in order to get this, make this work. And sometimes it's also not so stable, and and also most importantly, computationally expensive. It looks very simple, but when you code them, it's easy. But in reality, all this reversion and when you have a large number of parameters and samples, it takes time. So what our solution is to use optimization directly. You can write this as RSS using L2 norm, this square root of norm, and this value is the sum of this difference between observed and predicted, and that's your likelihood function. So once you have that, we can plug in the likelihood function with your data, give to optimization algorithm. So optimization is using this loss function to determine how good, how bad your parameters set up regarding to solve the problem. And the optimization procedure, just like this, you have, I don't know which this instrument is called, but you can have a lot of parameters to change continuously. And then different combinations give you some solution. You can ask your audience, so is this a good sound? And your feedback is good or bad. You can accordingly to change the parameter of those to adjust to the output of noise sound, and then determined by the audience feedback. Audience feedback is the loss function values to give you feedback. So you change that again until you reach to the optimized solution. Optimized solution will be your solution, the combinations of those parameters satisfy your audience feedback, okay, to give you the best feedback. In this case, it's the lowest value in loss function. Okay, so the minimize least square function is the way we can use. So if you have the loss function defined in this way, this is called the least squared method. If you have optimization engine, it's only give you the maximized value. You can put a negative sign in the object function. You search for the maximized likelihood, something like that. So you change your loss function in the opposite direction. Then you do this iteration internally. This certainly will have update procedure to update your parameters depends on the previous steps, and then the feedback of the loss function, the function evaluation. If it's okay, and you have a certain cutoff and to stop the procedure to give the solution output. Otherwise, this procedure will continue to determine the new parameters combinations based on the previous one, and there's a way to do this optimization. And the gradient descent is most commonly used gradient descent search method. It's search on the combinations of the parameter space. So if you have a two-dimensional space, so you have a x1, x2, and your loss function is the y, and the combinations of x1, x2 give you the higher and lower value of L. So you want to have a systemic way to search from the combinations of x, y to move to next step to find the lowest loss function value. So try to, on this map, you try to find the lowest point in this counter. And the way to search is to take small steps, and you have initial guess of XY position. In this case, you initialize the value here and you get Y, and then keep moving by small steps until you search to find the lowest value. Well, as I already showed you before, and there's a function called F minimum search, which is global optimization function for search for the combinations of parameters in the vector you gave here, and then the function definition is a loss function. So this particular function engine will just help you to find the best solution to satisfy the smallest value for that function. Internally, and it's more complicated than just what I said there. Let's play a video and see the introduction of Matlab related function optimization toolbox. So you see, there are many different ways to do this, and it depends on the applications complexity.
Optimization toolbox provides solvers for finding the maximum or a minimum of an objective function subject to constraints. This enables you to find optimal designs, minimize risk for financial applications, optimize decision making, and estimate parameters. We can use the problem-based approach to define the optimization variables and the bounds, set the objective, and then solve. On this problem, the solve function recognizes the problem is nonlinear, applies a nonlinear solver, and uses automatic differentiation for faster gradient evaluations. Optimization problems often have sets of variables or constraints, like in this production planning problem. We can define arrays of optimization variables and constraints and index with numbers or strings, resulting in readable and compact representations of large problems. You can use the problem-based approach even when some functions are not naturally expressed as optimization expressions. This problem's objective function requires solving an overview. You can convert this to an optimization expression and use it in a problem to be optimized. You can add integer constraints to linear problems involving variables which must take on integer values. This includes when the variables represent a yes or no decision, like whether a process is assigned to a processor in this scheduling example. In addition to solvers for nonlinear, linear, and mixed integer linear programs, Optimization Toolbox includes specialized solvers for quadratic programs, second-order code programs, multi-objective, and linear and nonlinear least squares. We can quickly solve large and sparse problems with thousands of variables. Here, a quadratic problem with over 40,000 variables is solved in around 30 seconds. As an alternative to the problem-based approach, you can use Optimization Toolbox with the solver-based approach. After representing your objectives and constraints as Matlab functions and matrices, the optimized live task helps guide you through this approach by indicating where to select the solver and insert your predefined Matlab constants. Optimization Toolbox works in conjunction with other Matlab tools. You can accelerate numerical gradient calculations using parallel computing Toolbox. You can compile your applications into apps or libraries with Matlab Compiler and Compiler SDK. You can generate portable and readable C code to solve your optimization problems using Matlab coding. Use this code to deploy applications to enterprise and embedded systems. For more information, return to the Optimization Toolbox page or use a link below.
Okay, so depends on your problem, and so there are a lot of adaptive procedures to select, for example, which algorithm, what kind of procedure you want to use, and to accelerate the search, and how many parameters you have, whether linear, nonlinear relationship are getting involved. So it's a huge research area, but for us, if we can define this loss function, it's already a huge success, because the rest of them, the numerical solution, we can leave them to either Matlab or R or Python packages. So for our applications, most important is to understand your question and define the loss function, and you know the search space and the parameter combinations. So those are the most important part we need to pay attention to. As I said, although this is beautifully theoretically to get the beta value with normal function equation, but in reality, in the implement of the package, for example, you click a button to get the beta values for the model fitting. Internally, they are using gradient descent algorithm, which to search for the minimized values through the quick slope to find the relationship between your values of your beta and also combinations of beta and the loss function values to find a way which you need some derivative, the calculus to get this which step to move into the search space. And we found the place that you can move quickly to the end of the search using the few steps. So their procedures have been well established. How can you find the next combinations values from the previous step and look at the slopes between each parameters with the loss function. And then you calculate those slopes and found the combinations and give you the quick descent to the lowest values. So those are the procedures that you need to have. Have some of these calculus to work it out if you know the shape of this. Otherwise, you have to use stochastic search. One of the examples is this. You have two variables, W and B, and this your loss function space, the search space. And you want to reach to this center of here, have a lowest value relatively. So your loss function, L, is a function of a beta, W and B together. So your initial guess somewhere, maybe here, the combinations, there's a -3 something and -3 something, B and W. Then you calculate the value, which is 13.5. That's your L function value. Then you calculate if I respect to B and then respect to W, what is our derivative for this partial derivation and the L value. Then you get that, and then you want to move negatively to that direction and with a parameter to see how long this step is. So this value will determine how fast you will move to next step. Okay, you don't want to be jump too much, or you don't want to be too conservative to make small steps, so make the whole procedure too low. So so this parameter can help you to change that speed. And gradually you move, you update your next value based on your previous W and the B values, and add these values and then move to next until you reach to the minimum. And then after that, there's no change because this value becomes too small, and then there's no further improvement for the L, then you can stop. At that time, the value of beta, B and the W is your solution. So the parameter here, I just indicated you don't want it to jump too much. You also don't want it too small. If you're too small, you may trapped to this local optimization point and not be able to search to jump to this global lowest point here. But if you jump too much, you just bounce around, the overshooting problem. Okay, so there's a link between gradient descent and Newton's method, and there's discussion about those slight difference between them. Okay, when you have a lot of parameters, so we have hundreds of parameters to define a single Y output, then you will quickly run into overfitting problems. For example, there are combinations of these different parameters to explain the price, and then looks like this fitting, and just all right, you use second term as quadratic power, and then you get this kind of fitting. Well, this is underfitting a little bit. That is overfitting because you are modeling the data points just too carefully, and then you lost the global trend, and then it's actually give you bad prediction power in the future for other models, for other data points. Well, so how can you decide and make sure those overfitting problem cannot can be solved, eliminated. The way is to find the power, for example, the values of the theta 3, theta 4. If they are too small, you just get rid of them. Overfitting, and also have the problem for classification problem. Okay, so this, this procedure, if you you use this procedure to eliminate some of these parameters which contribute too little to the overall fitting by set their values to 0. And this procedure is called regularization, and that we want to reduce the magnitude of values of parameters. So before regularization here, beta, you have every single beta have a value greater than 0 here and absolute value. But after the procedure, you reduce some of this to zeros. Okay. Regularization in mathematical statistics, particularly in the field of machine learning and the inverse problem, refer to process that introduce additional information in order to solve the ill-posed problem of preventing overfitting. So how can we introduce additional information? We introduce additional information in the loss function definition here. Let me show you. That's a loss function we already familiar with, right? We want to minimize this loss function, which difference between predicted and observed. Well, in this function, you have a set of data values. Now, this loss function is not only the contribution for the overall fitness now. It's also the beta values here in the function is also contribute to the overall fitness minimized. So you want not only by simply minimize the loss function value, you also want to consider the beta value. So if you have thousands of beta values, and the sum of this beta value make everything bigger than the over-dominate your gain of the loss function values. Because now you want to minimize both of these. You don't want a lot of beta values in there. If you set a lot of beta value to 0 and not change much, have not much impact on the loss function, then you achieve overall minimization for this combination. So this loss function becomes two terms. One is loss function itself, and another is beta, your parameters. That's the whole idea about this. Not a very elegant idea, but well, this is three Stanford professors. They just come up with this Lasso idea. There's a list, absolute shrinkage and selection operators. There's a name in 1996. So they minimize not only the loss function, not the least square, but also a function of beta value itself. And this, they use very simple function, which is L1 norm of beta. Okay, so remember what is L1 norm? L1 norm is in this beta value vector, you just absolute value of sum. So if you have a lot of small values, 0.03, 0.09 for all the thousands of individual least important variables, you actually make this L1 norm of beta greater. And also you have a normalized parameters to amplify this effects a little bit. Then that will give you the overall minimized function, a larger value. So you want to control for the values in the beta. You want to put a lot of small values into 10 into zeros. Then your total L1 norm of this term become smaller. And because this parameter you 10 to the 0 has less impact on the overall fitting. So overall, you will keep this still valid and small, and also you minimize the L1 norm for the beta vector. So that's the whole idea. Not too hard, right? Just add one term which finalize your parameter values. That's the lasso, okay? The other way to write it, just a different variable name. You always have loss function which error between observed and predicted. So that's linear regression, and you want to optimize this square. That's always here. And once you see lasso method, you always see this term, which directly plug in here and add into your loss function. And this is the L1 norm of your beta, your model parameters. And this lambda, just a parameter to adjust the contribution of this. If you think, okay, this term is more important, you make this lambda bigger. And it contribute more to the loss function, and you need to be more stringent to give the small values in the parameters. If you put it into 0, then lambda equals 0, then that's just a regular least squared optimization problem, and you don't have any restriction of the parameter. Okay, the same thing. I just gave you a slightly different way to write this. And L1 norm, okay, the sum of this theta, here use theta not beta as values. And then still that's a difference between predicted minus observed, the same as observed minus predicted, because you have squared there, so it doesn't matter. Still, this once you see lasso, and you always found, okay, regular term and this penalty term for the parameters. Okay. Well, what is ridged regression? Ridged regression, very similar to lasso, just change L1 norm to L2 norm. That's it. The way they write this is, in this case, they put the loss function regular term, that's a difference between prediction and observed in the end, but they put this penalty curve term for the parameters in front, and this is dot product. So this is a L2 norm. Okay. Still, they have lambda as a parameter to adjust relative contribution for these two terms. So when you see this plus L2 norm squared, basically squared norm. this is a rigid regression. So I don't have to explain that again because the concept of lasso is already, you know that, and the only difference is this. So what's the performance of lasso and rigid regression in terms of the overfitting problem correction? L1 norm will use this lasso to give you a sparse model. This gave you the solution for the overfitting problem, but the rigid regression will not. How can you understand this? So if you have combinations of parameter, for example, two parameters, beta 1 and beta 2, and then your best solution here. So both beta 1, beta 2 will contribute to that. In that case, both of them have some values. Well, if you use L1 norm to do this, so you want to have beta 1 plus beta 2 relatively small. And then if you do that in this unit squared, then the one will satisfy this relationship is in this tip point here. In that case, the touching point of your solution, you have a lot of solutions for combinations beta 1 to 2, but this particular position here make beta 1 0 into 1. Okay, and you only have beta 2 value. So if you require the solution, do you have many solutions? And one of them is the best one here, but because of the restriction of your L1 norm, so you want the solution which is inside this box. And also inside this box and also close to the optimum is your touching point of here. And if you use this as a solution, you minimize the value of B2 into 0. So you basically regularize B2 to 0, force it to 0, because you want to have a solution satisfied which inside this box. And then your best solution will be the touching point of this squared corner to the any solutions and close to the optimal. You don't want to optimal because you don't want to both beta 1, beta 2 have a value. This is not so obvious, but if you have thousands of parameters, and then this box will be this polygon, hyperdimension, hyperplane. I don't know what the shape looks like. It's like a object which have a lot of sparse, sharp corners, and any of the sharp corners touch to this overall solution will be the best, because it satisfied your requirement and also close to the potential overfitting optimized position. But anyway, so this just tells you why L1 norm and lasso will give you a sparse solution, because your touching point automatically cut a lot of parameters into 0, not to reduce the parameters into 0. Well, the rigid regression, because it uses this unit circle and the touching point cannot guarantee it's one of the parameter becomes 0. So we still have some values in there. Well, you can combine the use both L1, L2 put together to make a combined loss function. This loss function include both L1, L2 norm, which you basically you use rigid regression plus lasso at the same time. This is called elastic net regression. Again, all this optimization procedure has been implemented in Python, R, Matlab, whatever. Is so generalized so far, and there's many citations and different variations which derived from this idea. And you can, for example, define your own penalty term to add the penalty to these extra values for the beta. You can create your own method. Well, this idea is all from Lasso and very similar, and they found many different applications, different derivations, and in different applications. That's all for this week's lecture, and we will have a computer session to practice some of this, and we can do Lasso, and we can create a problem with thousands of the parameters to do the prediction, and so how Lasso can be used to set a cutoff, see how many parameters I really want to have values from 1,000, I will reduce to 75 or 85 or 150. How can we do that by selecting different lambda or other values? Okay. Yeah, I'm surprised we don't have single cell context today, but that's all the regression and the Lasso idea. And I hope it's useful for our later lectures. And, okay, and other questions? All right. Online students, are you okay? Okay, great. Then see you each other Thursday.